Hello everyone. In this video we are going to talk about the Rayleigh's method, which is one method for calculating the fundamental natural frequency of the system, the fundamental frequency or the first natural frequency of the system, the lowest one, the smallest one. And this is an approximation method. So we're going to see how this method works. We're going to derive the Rayleigh, what we call Rayleigh quotient, and we're going to use it for a 2DOF system here, and we're going to compare the result of that against with the accurate, the analytical solution. So first of all, why should we ever think of approximation methods for natural frequency of the systems that are more than 1 DOF? The reason is the computation, okay? When the systems are complicated and they have so many degrees of freedom or infinitely many degrees of freedom like continuous systems, then calculating these natural frequencies, especially the first one, which is the most important one, is quite a bit demanding computationally. So you might want to use approximation methods like Rayleigh rates, and other methods in the literature to come up with the first few natural frequencies and mode shapes, so you can avoid them in your design. Okay, so that's one reason. Now let's see how this method works. So here, since we are talking about the natural frequencies, so we assume the system has a free vibration, not forced vibration. And we know systems in free vibrations, they have a harmonic motion. Now it could be sustained oscillation or damped oscillation, okay? And then if that's the case, then x, let's say if this is the variable of the system that you want to find out, is x of t, this is typically something like a times sine omega t or cosine omega t, or a combination of both, okay? It's a harmonic response like that. If you take time derivative, then velocity v, right? Let's say x here is position. Then v, which is the time derivative, or x dot, that is going to be a omega cosine omega t. So if you look, maximum of x is a, but maximum of v is a times omega. So I can say v max is omega times a max. And what omega? Omega n, because the system is oscillating with this natural frequency. So this should be what? Also natural frequency. That's where you get this formula from. Okay? Now, here we're going to look at the energy method. So we look at the principle of conservation of energy, right? We assume that the system is basically, it does not have any damping or any source of removing the kinetic energy of the system or the mechanical energy, and the mechanical energy is conserved. So here, the case that we are looking is no damping, basically. We just want to find omega n, not like a vibration where we had omega d, if you remember the damped natural frequency, which was omega n square root 1 minus basically zeta squared. So we are right now after this one. Okay, if that's the case, then we can say that the maximum kinetic energy of the system is equal to the maximum potential energy of the system. Like, consider a pendulum, right? And in this pendulum, when it goes to the maximum angle right up here, you have maximum P, but K is 0. And when it comes down here in the middle, here K is K maximum, but potential energy is 0. And since some of these two are equal, then we can see that K maximum is the same as P maximum. Or if it's a mass spring system, doesn't matter. K max equals P max as long as there is no damping or no non-conservative force in general. So what is K max? K max equals 1/2 of V max transpose M times V max, when v and x in general could be vectors. Here, the example I showed you is a scalar. X was a scalar, but in general, this x could be a vector. Why? Because your system, as we said, in general, has more than 1 degree of freedom. So your x is in general a vector like this, and so your V is going to be a vector, and still this relation exists between them. So now you have to write your kinetic energy into matrix format. So it's going to be 1/2 vector Vmax transpose times M, which is a matrix, and we call it the mass matrix of the system, times Vmax. And for Vmax, you replace it with omega n x max. So here you have 1 omega n, here you have 1 omega n, so you get 1/2 omega n squared x max transpose m x max. And P max is going to be 1/2 x max transpose k x max, and this k, we call it what? The stiffness of the system. So if it is, for instance, a single DOF system with a simple spring and a simple mass, right, and this is x, and this is k, and this is m, you know, in this case, k is simply what? 1/2 Vmax times m times what? V, and since they are scalars, you write it as 1/2 mv squared, right? And that is your kinetic energy. Now, since it's a scalar in this case, Vmax transpose and Vmax are the same thing, okay, in general. So transpose has no effect. And P in this case comes from the stiffness of the spring times 1/2 times x squared. So you write it as this. And you can also write it as 1/2 x transpose times k times x. Right? So you see here, x is k is a scalar, m is a scalar, but in general, for several degrees of freedom, they can be what? They can be vectors. So these are the formulations for them. We set them equal now, and from here, we are going to solve for what? For this omega n squared. If we do so, it is going to be x max transpose k x max divided by x max transpose m x max. And this ratio that you see, we call it the Rayleigh's quotient, and from here we can find the square of the natural frequency of the system. Okay? Yeah? So, this is when what? This is when, this is good formula, and it's going to be accurate when this x max only has one of the mode shapes of the system. For a system with several degrees of freedom, like this one has two, this x vector, if it's just one of the mode shapes, if we here call the mode shapes like omega 1 and x1 and omega 2 and x2, if the displacement of the system at any point is just what? Is just one of these mode shapes, so it's like some c times x1 times sine of omega 1t, it's just one of the mode shapes is activated. This solution, as we'll see, will give us perfect, accurate result. But in general, the solution that you get in the system is not exactly one of the mode shapes. Most of the time, it's a linear combination of the mode shapes. So it is going to be something like this. x1 times 1, here, the coefficient of that is like 1, plus x2 times some coefficient c2 all the way to as many frequencies as you might have, depending on how many degrees of freedom that you have. So this does not go to infinity. This might end like at cnxn, okay, where n is the degrees of freedom of the system. So you can write it like that. And what are these coefficients depend on, right? You might even call this c1, but here everything is divided by c1, so it's kind of normalized. But the c1, c2, cn, how do we calculate them? They depend on the initial conditions. They depend on x of 0 and what? On x dot of 0, right? So they depend on this. If you remember, I have a video on my channel under vibrations playlist. Look here, if you go under vibrations playlist, one of the things that I clarified for you is this guy. What do mode shapes mean? That's the meaning of mode shapes, okay, right? And If you go to this video around time 15 or 16 minutes, you see that here V1 and V2 are those mode shapes in this case here, and x0 is the initial condition. So here we assume that x dot 0 is 0, just x0 is non-zero. You see that the coefficients that you need for the solution of the system, a v1 times cosine of this square root of lambda here is omega 1. Right? These coefficients A1, A and B, which correspond to our C1 and C2, they are coming from what? They are coming from the modal matrix inverted multiplied by the initial condition. So it's the initial condition that determines what? These coefficients. If the initial condition x0 is exactly matching V1, then A1 is like 1 and A is 1 and B is 0. Right? So if you start with an initial condition corresponding to first mode shape, then you'll get what? Only first mode shape activated. If you get it exactly the same as second mode shape, then only second mode shape will be activated. But if it's none of them, then a linear combination of the two will be activated, right? So I explained that. If you want, you can take a look at it. So here, in general, when the solution is several of them together, because your x0 does not match any of the mode shapes, then you write your x max as what? As a linear combination of them, or x in general, right? And from there, if you go, multiply it by, make a transpose of it, multiply m and then by x. So here we are trying to calculate this denominator term here. You get what? You get basically x1 transpose m x1 c2 squared x2 transpose m x2, and if you now go and calculate the numerator term, you're going to get a similar thing except replacing m for k. So if you plug in these two into this Rayleigh quotient and simplify, you can see that your omega n squared is going to be omega 1 squared times what? Times 1 plus c2 squared times omega 2 over omega 1 squared minus 1 all the way. And to get to this equation, we use also another property, and that is xi transpose kxi is omega I squared xi transpose mxi. And this comes from the definition of what? The definition of the eigenvalues and eigenvectors, right? So if omega i's and xi's are eigenvalues the omega squares are eigenvalues lambdas, and these x's are eigenvectors, then we can write this relation between them, right? We know that's the solution. And so you get this equality, right? And now here, if you look, if the C2 is 0, and the reason is x0 is perfectly equal to x1, and what? And x dot at 0, let's say, is 0, then C2 and all the other C's will be 0, so you see your omega n squared is going to be exactly omega 1 squared. As I said, you get exact solution. But if this condition is not satisfied, this is not equal to any of the mode shapes, then guess what? The estimate that you will get will always be bigger than omega 1. It doesn't matter what you use to calculate the Rayleigh quotient, what kind of x you use in it, you always get what? You always get a bigger estimate than omega 1. Okay? So let's see that with an example. Let me clarify that with an example. So here we have this 2-DOF system, 2 masses and 3 springs, and K, 3K, K, and here these masses are rolling on the floor, so there is no friction. And here I show you both exact solution and the Rayleigh quotient. So we're going to solve it parametrically, M2, M, K, 3K, and K, right? So let's first find the exact solution. What is the exact solution? We'll look at the free body diagram of this mass with 2m here. And for simplicity, we assume that x1 is bigger than x2, right? It does not violate any equation. Even if we say x1 is less than or equal x2, the result is going to be the same. So here we just make an assumption. If that's the case, since this mass is moving this way, this spring is being stretched, so it's going to pull back, and the force of it is going to be k times displacement right minus left, which is x1 minus 0, so just x1. Since x1 is bigger than x2, this 3k is being compressed, so this is going to push back, and it is going to be the constant of it, 3k times the difference of the two displacements, right? And as I said, you have mg and n, so you have 2 mg and n, but in the x direction you only have the spring forces. So if you write it, 2m x1 double dot equals negative k x1, negative 3k x1 minus x2, so that is this equation. Then if you look at the 1m free body diagram, that is very similar. The reaction of this force is applied to the right, so that is 3k x1 minus x2, and this spring is going to be compressed, so it is going to push back with k times x2 minus 0. And again, it has mg and n, but in the x direction it's the spring forces that are acting. You see, one of them is positive, one of them is negative, and this is the equation for the second mass. Now we're going to arrange it in a matrix format, so we're going to write it as m times x double dot e plus k times x equals 0, right, where x vector is the vector of x1 and x2. You see the mass matrix is going to be 2m 0 0 m, and the k matrix is going to be 4k negative 3k negative 3k 4k. Okay, so these are our mass and stiffness matrices. If we want the eigenvalues and eigenvectors, we multiply both sides by m inverse, right? If you do so, then this is your m inverse times k matrix. You find the eigenvalue and eigenvectors of this. The first eigenvalue, the square root of that, of course. So this is not the eigenvalue, this is the square root, because it gives you two lambdas, lambda 1 and lambda 2, the two eigenvalues. Omega 1 is what? The square root of lambda 1. Okay, the first frequency is 0.8092 square root k over m, and the first mode shape is this guy, 1.115, 115 and 1. The second omega, which is the square root lambda 2, the second natural frequency is 2.312 k over square root k over m, and the second mode shape is negative 0.4484 and 1. Okay, so these are exact solutions. This is what we wanted. The first fundamental, the first frequency, the fundamental frequency is that number, depending on how much k and m are. Now let's go ahead and what? Let's go ahead and apply the Rayleigh quotient and see what value we get for omega 1 squared. So the formula was what? X transpose kx over x transpose mx. And so we don't have this x max, we don't know it, so we're just gonna put some number for it, some vector for it, and see what we get. So this x max could be any vector 2 by 1, because x is a 2 by 1 vector. So we're just gonna plug in one number for x1, one number for x2. This is what we think it might be the x max of the system, and we get some approximation for omega. So what are the approximations? The problem said one time use 0.5 and 1. And you might say, where did he get this one from? Does it make any sense? Well, here, since this guy is twice as heavy as this one, you might think, and the k's are symmetric, you might think that because this one is twice as heavy, it might move half of the other one. So if this one moves x2 equal 1, this should move x1 equal to 0.5, equal to the ratio of these two. Okay, the heavier mass moves less, and with the same ratio of the masses. So if I plug that into this formula, multiply by k transpose of that, right, you see, an m, and simplify, I get omega 1 squared equals 4k over 3m, or take a square root, you get this number here. And clearly you see that is bigger than this. The actual number is 0.809, here is 1.15. So you see, I got what? A bigger value, right? Now, if I'm lucky enough that I exactly plug in what? If I exactly plug in for x max one of the mode shapes, which mode shape? Mode shape 1. If I exactly plug in mode shape number 1, right, look what happens. If I plug that in, seems like here I made a mistake. That's not 4k over 3. Yeah, that problem always happens when you try to copy and paste your previous formula. Sometimes you forget to fix those, right? So I just copied and pasted and changed all of the numbers except for that one. So the number that you will get is 0.7039. You can try it with MATLAB. And when you solve for omega 1, take a square root, you get exactly omega 1. You see, so how accurate you get the solution for the omega depends on what kind of value you use for this vector x max. Because you don't know it, right? You have no idea what that one is unless you solve it analytically. And so here is just an approximation putting a value for this vector x max, and depending on what you use, you're going to get different solutions, okay? But the thing is, the solution is always, if you don't exactly use these mode shapes, which you never know until you solve for them, the solution is always an overestimate for the omega. It's always what? An overestimate. You will never go underestimate. And that is a good thing. Why? Because as I mentioned in one of my previous videos, in real life, the physical frequency, the operation frequency that you use in real life is typically what? Much bigger than omega 1, or the first few frequencies, especially omega 1. So if your estimate is bigger than omega 1 and you go bigger than that, then you're sure that whatever you chose for operating frequency is definitely bigger than omega 1. But if you underestimate omega 1 from this formula, so let's say the actual omega 1, let's go with numbers, the actual omega 1 is 1000. Rayleigh quotient gave you maybe 1300 or 1400. So from here, you pick your operating frequency to be maybe what? Maybe, I don't know, 5000, 4000, 3000. But sometimes you don't want to go way above these numbers, so you just what? You just go to 1600. That's not really a safe thing to do, but let's say you don't want to go much higher than the natural frequency because it is high by itself. So here, because this is bigger than that and this is bigger than actual omega, I'm safe, right? But if Rayleigh quotient gave me an underestimate, so it gave me what? It gave me 700 instead. And I say, well, 700, I go above 700, no worries. I go to maybe 1000 or maybe 1050 or something, 1100, 900. Then I'm very dangerously close to my natural frequency. Okay, so it's better that it's overestimating my first frequency than underestimating, and it does that. But how accurate, that depends on what? That depends on these numbers that you plug in. And you might say, whatever I use, do I always get an overestimate? Yes, you can see in this formula that this term here is clearly positive because omega 2 is bigger than omega 1 and this is C2 squared. So this ratio is clearly bigger than 1. The whole thing is bigger than 0. So yes, the answer is it doesn't matter. Now you might wonder what happens if, in this case, I pick the second mode shape, right? If I pick the second mode shape, which is that negative 0.44 and 1, what do I get if I plug that one in? Well, let's do it. Okay, so you can see here that I plug in the second mode shape for x max, and when you go and simplify the Rayleigh's quotient, you get omega n squared equals 5.35 k over m. You take the square root, and guess what? You get the second natural frequency. You see it was 2.312 square root k over m. Now this is just for round-up errors, is 2.313 k over m, right? So this Rayleigh quotient in general is not just going to give me what? The first natural frequency. It can give me any natural frequency as long as this vector that I use in the formula x max is what? Exactly equal to or very close to one of these mode shapes. So as long as I put those, it's good, but if I don't, it always gives me what? An overestimate of the first natural frequency. So this is the comparison with exact solution against Rayleigh's method for fundamental frequencies, especially the first one. And by the way, equations and pictures are taken from the book Theory of Vibrations with Applications by W. Thompson and colleagues. Thank you so much for your attention. I'll see you in the next video.